Hi everyone, welcome back. In the last few sections we've taken a first look at differential equations. We introduced what a differential equation is. We've looked at how to verify a given function is a solution to a differential equation. And in the case of separable differential equations, we've come up with techniques for solving them. In this section I want to look at how a differential equation arrives as a model of a particular situation, particular phenomena. And in this case we're going to focus on population growth. So let's have a look at the natural growth model. Now this is revisited because it's one of these things that you probably saw in high school mathematics, and again you saw it in Calculus 1. We're revisiting it again now because it's one of the most basic models for population growth, and in some sense it's one's first encounter with a differential equation. So what is the natural growth model for population? Well, the idea is fairly straightforward. It is you make the assumption that the rate of change in your population is proportional to the amount that's present. So in this case we're letting P denote the population at time t. So P is our population at a given time t, and we're saying that how fast the population changes, its rate of change, is some constant multiple of the amount present. So it's proportional to the amount present. So this is the rate of change, and this is the amount. Actually, just the P is the amount present. So if you have a large population, you expect it to be growing rapidly as well. If you have a small population, you expect the growth rate to be fairly small. So you expect the growth rate to be proportional to the amount present. Now that's just a very simplified model for how we may think that populations change. So now we're staring at a differential equation. This is the natural growth model. It's a differential equation. And our goal is to figure out what is the function that satisfies the equation. What is the function that gives us the population at any time t? Now this is a separable equation, so we can use our techniques from separable equations to solve this. So the idea was you separate the variables, move everything involving p to one side and t to the other side. So this would be 1 over p dp is equal to k dt. And now once you've separated the variables, then you integrate both sides. Now the integral of 1 over p dp is ln absolute value of p, and the integral of k, well k is a constant of proportionality, so the integral would just be kt in this case. And then we have our constant of integration c. Now this is our general solution to the differential equation, but we can rewrite it. We can say, well, we'll take e to the power of both sides. So e to the ln of absolute value p is just absolute value p, and we can take e to the kt plus c. Now at this stage we can notice that e to the kt plus c is e to the c times e to the kt. This, since c is just a constant, it was our constant of integration, e to the c, it's also just a constant. In this case, e to the c will always be a positive value. So the absolute value of our population function is always some positive constant times e to the kt. But we can remove the absolute value signs if we want. Replace e to the c with a, where we can have a being plus or minus now because I've removed the absolute value signs. So this is e to the kt. So what we've done here is we've just said where capital A, this constant, is plus or minus that constant obtained from the constant of integration. So what does this mean? It means we have our solution now to the natural growth model. If a population satisfies this model, that its derivative is equal to a constant times itself, then the function must be an exponential function with some constant out front. Now for population growth, so we'll only think of these things as being positive quantities anyway, so a will generally be a positive value for us. But just noticing here that in the context of just here's a differential equation and here's a solution, that some solutions could have negative a values. Now, what is a in this case? Well, we can notice that P of 0. If I take the population at time 0, plug 0 in, then the right-hand side becomes e to the 0, which is just a. So that constant a that's sitting in front, it's just the initial population, which we typically call P naught. And that's the initial population. So we can write our solution as P of t is equal to P naught e to the kt, where P naught is our initial population. Okay, so we've started with a differential equation, and from that differential equation, we've got an explicit solution for what the population function has to be. P naught is the initial population, k is this constant of proportionality, or the growth rate, and that could be found by taking samples of the population at different times, and you could then solve for k. Now there is another way to write this differential equation. We could write it as dp dt divided by p is this constant k. And this is the relative growth rate, this quantity on the left. It's the growth rate divided by the population. And so what the natural growth model is really saying is that the relative growth rate is constant. So it's just another way to state this natural growth model equation. Rather than saying the rate is proportional to the amount present, we can say the relative growth rate is constant. Now, phrased in this way, what we're really saying is that if we have any population whose relative growth rate is constant, then that population must be growing exponentially. Must be growing exponentially. So a population with relative growth, constant relative growth rate must be growing exponentially. That's just a very succinct way to summarize what this natural growth model is saying. Now there's a problem with this natural growth model in that if we look at the solution down here, we see that the population is growing exponentially indefinitely. As time goes on, the population is still growing exponentially. Now you may think that, well, this can't possibly be the case. Populations don't grow without bound. There could be some other issues resulting in changing the growth rate, and that could be things like limited resources, limited space, limited food supply. There could be disease. There could be all of these other things that come into play in determining how a population grows. And this model does not take those things into consideration. So this gives rise to what is known as the logistic growth model. The idea here is that with the natural growth model, things should break down at some point. We can't have a population grow indefinitely. So in searching for an improvement to this natural growth model, we maybe make some additional assumptions. Rather than just that the population grows proportional to the amount present, we should also think that there's probably some carrying capacity for the population. That is the maximum amount that the population can reach before it just stops growing. This is known as a carrying capacity for the population. Now, how do we incorporate that into a model? Well, the logistic growth model is this way of incorporating those two ideas. One is that the growth rate should be initially close to being proportional to its size. So at the very start, when you've got a small population, it should grow roughly proportional to its size. This is the natural growth model part. But this can't continue forever. And again, this is due to limiting resources. So, for example, we could outstrip the food supply. So at some point, the population ceases to grow exponentially. So what happens is then the environment may introduce some constraints, and this constraint that the environment introduces may be some limit on the carrying capacity of the population. So we're saying then that there is some maximum amount that the population can reach when it ceases to grow anymore. And so that we're saying here then that the limit as t goes to infinity of p of t, the population, should be m, the limiting value of this. Now, how do we take these two conditions and model them? Well, here's the simplest way to do it. It's to say that the rate of change is, and if you ignore this 1 minus p to the m, you see that it's just proportional to the amount present. But there is this 1 minus p to the m term. So why is it of the form 1 minus p to the m? Well, the idea is if p is small, we would like dp dt to be roughly kp. If p is small, then p over m is small, really small, close to 0. So 1 minus p over m, that's really small. So this is roughly 1. So dp dt is roughly just kp. So this thing is approximately 1 if p is small. So that means that we're getting this first condition satisfied. What about the second condition? Well, this is approximately 0 if p is close to m. P is close to m, p over m is close to 1, 1 minus 1 is close to 0. So this is close to 0, so it means the population's not growing. The rate of change in the population would be approximately 0. Now there's some additional things to note here, that if p is bigger than m, then 1 minus p over m is negative. So not only does this model say that if p is close to m, then the growth rate is roughly 0, but it says, suppose your population was slightly bigger than the carrying capacity. Then 1 minus p to the m is less than 0. That's negative. And the k times p, well, the population is positive. K is a positive constant, so these things would be positive. So your rate of change would be negative. So your population would be decreasing. If you had a population that exceeded your carrying capacity, then your population would be decreasing so that it approached the carrying capacity eventually. Alternatively, if p was p was smaller than m, then 1 minus p over m is bigger than 0. So all of these quantities, if p was bigger than m, then 1 minus p over m is bigger than 0. So this is positive, p is positive, k is positive, all those things are positive, so the population is growing. So if your population is lower than your carrying capacity, then your population is increasing. So either you start out below your carrying capacity, in which case your population continually increases until it approaches your carrying capacity, or if you start out with a population larger than your carrying capacity, then your population is going to decrease to approach the carrying capacity. So that's what this model represents, and that seems to be a better choice for a model than just the natural growth. This takes into consideration that there are depleting resources and they will affect the population growth as well. So there's a couple of things I want to do with this logistic growth model now. I want to maybe do some qualitative analysis on this, get some pictures drawn, what kind of function satisfies this differential equation. And then we will do an analytic calculation where we actually explicitly find the form of the function that satisfies this. So first let's look at a qualitative solution to the logistic growth model. So what do I mean by qualitative solution? I mean just get a rough idea of what the function looks like that would satisfy this. What is this population function? What does it look like? Well, let's start with the p dt is equal to kp 1 minus p over m. Then we'll start with the equation. What does that tell us? Well, let's just do a sketch of population versus its derivative. Now, if it's population versus derivative, then what we notice is that, well, that's this equation here. The rate of change is quadratic in the population. It's quadratic in p. So what I'm going to do is I'm going to plot this here, and it's just going to be a parabola. It's got a root at 0. So when p is 0, the derivative is 0. When p is m, the derivative is 0. And so it's got to be a parabola. There's a negative in front of this p, so there's a negative p squared term when you expand this out. So it's got to be parabola opening downwards, passing those through points. So it looks like this. And it continues on both those directions. Now, where does it reach its maximum? Well, if you know two roots of a parabola, you're going to get the maximum right in the middle. So the maximum occurs at m over 2. That's the maximum of the derivative. So what we've done here is we've plotted the derivative of p with respect to t, the derivative of the population, against the population itself. What we ultimately would like to do is get a graph of the population function, so P versus T. So what can we do here? Well, I look at the horizontal axes in the first diagram and I see there's special things happening at 0, at m over 2, and at the carrying capacity m. So there's our carrying capacity m. Now we eventually expect that the population will, as time goes on, will approach that horizontal line here at height m. So this should be a horizontal asymptote for the functions that, the various different functions p, depending on initial conditions and whatnot. What else can we get from this diagram? What I'm going to do is I'm going to look back at the diagram here. On this interval from p between 0 and m over 2, what do I notice? I notice that dp dt is positive, and I notice that dp dt is increasing. dp dt is increasing in value. As p moves from 0 to m over 2, dp dt is getting bigger and bigger and bigger and bigger. If dp dt is increasing, then what does that mean? It means that the second derivative is positive, or in other words, p is concave up. So I go over to my plot of p versus t, and I notice that between p values from 0 to m over 2, p is concave up. It's increasing and it's concave up. So it starts at some initial point, and it's got to be concave up and increasing. Now it hits a value of m over 2. Then what happens? I'll switch colors here. What's happening on this interval? On that interval, dp dt still positive, so the function p is still increasing, but dp dt is decreasing. And so that means that p is concave down. So it's going to switch here, still increasing, but it's going to be concave down. So this is concave down. This is concave up. We have our carrying capacity here. This is our carrying capacity. And right here was our initial population, whatever it is. Given in the problem, I just pick some random point. If it's down here, then the function p versus t looks like this. It starts at your initial population, it increases, it hits its maximum maximum rate of change when you're half the carrying capacity, and then the rate of change starts to slow down. But the population is still increasing, and it's approaching the carrying capacity. So here we had an inflection point. That was the place where the second derivative of p is 0. And we can see that right here. We've got a plot of the first derivative versus p. The second derivative is 0 at m over 2. So at p equals m over 2, there was an inflection point. What's happening right at the start? Right at the start here, this is approximately exponential growth. When our population is pretty small, then we get approximately exponential growth. So it's starting out what is approximately an exponential function, and then it sort of turns into this stretched sort of S-shaped function called a sigmoid function. So that's what we can get just from looking at the differential equation and do just a bit of qualitative analysis. We haven't really solved for anything here. We've just noticed that things are increasing, decreasing inflection points. If I started a little bit higher up here, then I know that when I'm above m over 2, it's going to be concave down. And so our solution would look something like this. If I started a little bit lower, it would be concave up for a bit until we hit an inflection point. So it would go something like this, hit an inflection point, and then approach the carrying capacity. What if I started above the population? If I started above the carrying capacity, then my solutions would have to come down to the carrying capacity here. So we get a lot of information, qualitative information from the differential equation. We know roughly what the solution should look like. We still don't have analytic representations of these curves. That's what we're going to do next, but at least we have qualitative solutions, what they roughly look like. So now let's go ahead and construct an analytic solution. So we start with our differential equation, dp dt is equal to kp 1 minus p over m. We'll separate variables. There actually is no variable t on the right-hand side, so it's just going to be a constant left over there. Everything else moves to the left-hand side. So that's 1 over p times 1 minus p over m. dp is equal to k dt. I'm just going to clean things up a little bit over here. I'm going to multiply through by m top and bottom. So I get m minus p dp is equal to k dt. Our goal is to now integrate. Integrating the expression on the left, well, that's a rational function in p, so I can use partial fraction decomposition. I have to figure out what those the numerators are, and then on the right it's, well, the antiderivative of k with respect to t is kt, plus our constant of integration. Now what are the numerators here that will make this decomposition work? Well, you can stick in arbitrary values like capital A and capital B and do the technique for solving for those constants, or you can just notice that in this case, if I put 1 above each of them and then add them up to put them over a common denominator, take m minus p, put it up here, take p, put it up here, when I add them up I just get m in the numerator. So it turns out that 1 and 1 are the numerators here. So in other words, you can eyeball this. If you couldn't eyeball it right away, don't worry about it. Just throw in some constants up top and you can solve them. So now I can anti-differentiate. This becomes ln absolute value p, and then minus ln of m minus p is equal to kt plus c. So there's our solution. It would be nice to have this represented just in terms of p alone. So what we can do here is we can say, well, this is, using properties of logarithms, this is p over m minus p is equal to kt plus c. Now I'd really like to flip the argument of the logarithm over, so m minus p is on top. One way I can do that is I can stick a negative out front here at the cost of multiplying both sides by a negative. Now once I've stuck the negative out front, I can move that into the exponent as a negative 1. And if I move it up to the exponent as a negative 1, then that allows me to write this as the logarithm of m minus p over p is equal to negative kt minus c. Now I can take the exponential of both sides, and I get absolute value of m minus p over p is equal to e to the negative kt minus c. I'm going to do a couple of things here. One thing I'm going to do is I'm going to say, well, e to the negative kt minus c, I could take that negative c, now watch what happens, and just split it up so that it's e to the negative c times e to the negative kt. But e to the negative c, that's just a constant. It's actually a positive constant because exponentials are always positive. But I've got an absolute value here. So what I can really do, and it's much the same thing I did with the natural growth solution, is I can replace that constant with an a, and then say, well, a can be plus or minus. So that will allow me to get rid of the absolute value signs. So what we have is where a is equal to plus or minus e to the negative c. Now at this stage, we can divide p into each piece, so that's m over p minus 1 is equal to a e to the negative kt. And now solving for p, I get m over p is equal to 1 plus a e to the negative kt. And finally, taking the reciprocal of both sides, I get p over m is equal to 1 over this side. But I can take the m that's in the denominator of the p and move it up to the numerator of the other side, and I get that this is the solution, the analytic solution to the logistic equation. So this is our solution for p. We started with the logistic growth equation, and we've come down now to our solution, where m is the carrying capacity, and A is a constant that arose from the constant of integration. So it is a constant. So depending on the given population, your initial conditions, that will tell you what the value A is, and M is your carrying capacity. K is your growth rate as well, so that's another constant. And K is the growth rate. All right. So we've seen two ways to look at the logistic growth equation. One is this qualitative way where we got the rough idea of what the sketch of the solutions look like, and then we've got the analytic way where now we can immediately see explicitly what the solutions are in analytic form, and we can use this to then predict values, what's happening 3 years later, what's happening 5 years later for a given population in a given situation. All right, that's it for this section. Thanks very much for watching, and we'll see you again next time.